In the diagram, you can see that a particle is connected at the end of a rod and the other end of that rod is pivoted at the center of a circle of radius r. If we start its animation, we can see that the particle is rotating on a circular track, and during its motion, it is changing its central angle continuously. Let the particle start its motion on the circular path, and after time t1, it makes an angle θ1 with x-axis. And at another instant of time t2, it makes another angle θ2 with x-axis. Then the difference between θ2 and θ1 is called angular displacement in time interval t1 and t2. The difference between θ1 and θ2, which is delta theta, is called angular displacement. When the difference between t1 and t2 is very small, such that delta t approaching to 0, then delta theta will also approach to 0. For very small values of delta theta, the angular displacement is a vector quantity. And for the larger values of delta theta, the angular displacement is not a vector quantity and it is considered as a scalar quantity. During the anticlockwise rotation of the particle, the angular displacement is assigned positive value and it is measured along the axis of rotation of the particle, which is passing through the z-axis of the three-dimensional plane in this animation. If we flip over the axis of rotation in this animation, it seems as if the particle has started to rotate clockwise. In this scenario, the direction of the angular displacement is assigned negative sign, although it will be directed along the z-axis having negative values. The big flaw with angular displacement is that it is not treated as a vector quantity for greater values of theta. The reason is that the commutative properties of vector is invalid for greater values of angular displacement, means the greater values of theta. Let's perform an experiment with a die to check whether the commutative law of addition holds for angular displacement or it doesn't hold. For this purpose, I am selecting a die in three-dimensional plane. I'll rotate this die, means I'll make the angular displacement of this die first of all about x-axis, and then I'll make its angular displacement about y-axis. And I just want to check what are the effects on the face which is along z-axis. So let's start it now. First I'm rotating it about x-axis, means I am producing angular displacement about x-axis, which is red colored here. 90-degree rotation I am going to give it here. It's almost 90 degree. Not perfect, but it's almost 90 degree here. Now in the second step, I am going to rotate this cube 90 degree about y-axis. The y-axis line is green colored here. It's almost 90 degree. So I can see that in resultant I got the face of the die with 4 dots along z-axis. Now let's perform these experiments in another way. First of all, I shall produce angular displacement of 90 degree about y-axis and after that I'll produce an angular displacement of 90 degree about x-axis, and I want to check whether I'll get the same results. or there is some difference? I am rotating it along y-axis first of all, which is green in color, by 90 degree almost. So this is almost 90 degree here. Now I am going to rotate it about x-axis at 90 degree. So what are the results along z-axis now? I am getting the face with two dots along z-axis. So it's clear from this experiment that for the greater values of theta, commutative law of vector addition is not holding good in angular displacement. So for greater values of theta or the bigger values of theta, angular displacement is not a vector quantity. In System International of Units, angular displacement is measured in degrees, radian and revolution. Also, 360 degrees is equal to 1 revolution, which is equal to 2 pi radian.